Maxwell's Bridge. So before going to Maxwell's Bridge, we already know that bridge circuits are extensively used for measuring component values such as the resistance, inductance, and capacitance. Bridges are also used for measurement of frequencies, phase, temperature, etc. A bridge circuit consists of four arms. It may be with capacitance, resistances, or impedances, forming a closed circuit with DC or AC source of current applied to two opposite junctions and a current detector connected to the other two junctions. The bridge circuits use the comparison measurement methods and operate on null indicator principle. The bridge circuit compares the values of the unknown components with that of an accurately known standard components. Thus, the accuracy depends upon the bridge components, not on the null indicator. Hence, high degree of accuracy can be obtained using bridges. In a bridge circuit, when no current flows through the null detector, which is generally a galvanometer, then the bridge is said to be balanced. The relationship between the component values of the four arms of the bridge at the balancing is called bridge balancing condition or the balancing equation. This equation gives us the value of the unknown component. Each of the circuit element is arranged in one arm of the bridge. When the bridge is balanced, that is, a zero response is obtained from the null detector, or there is a calculable relationship between the values of the elements in the arms given by Z1 Z4 is equal to Z2 Z3. This is nothing but the product of the impedances of the opposite arms will be equal. In an AC bridge, along with the magnitude of the impedances, the phase angles, the sum of the phase angles of the opposite arms must be equal. A DC bridge employs resistances in its arms and the source of current is DC. In AC bridges, the arms have resistances, capacitances, inductances, etc. The supply used is the alternating current. The detector used in AC bridge is either a vibration galvanometer or headphones, whereas a DC bridge uses the galvanometer, D-Arsenal type of meter. As we already seen, AC bridge which is used at audio frequencies or radio frequencies are commonly determined by means of various AC bridges. The impedance at audio frequency or radio frequencies are commonly determined by means of the AC bridges. An AC bridge in its basic form consists of four arms, source of excitation, and a balance detector. Each arm consists of an impedance. The AC bridge is similar to DC bridge except that the arms are impedances, whereas in DC bridges the arms are of resistances. The galvanometer is replaced by a detector. The balance detectors are commonly used for AC bridges are the headphones, the tunable amplifier circuits, vibration galvanometers, etc. The source is an AC supply which supplies AC voltages at required frequencies. For high frequencies, oscillators are used as the AC source. The general form of AC bridge consists of one arm impedance Z1, other arm impedance Z2, the third arm the impedance Z3, the fourth arm impedance Z4 with a detector connected between the arms carrying Z1 and Z2, and the source of excitation connected between junctions of Z1, Z2 and Z3, Z4. The impedance is the product of impedances Z1, Z4 is equal to Z2, Z3. In terms of admittances, we can give it as Y1, Y4 is equal to Y2, Y3. So the product of impedances of one pair of opposite arms must be equal to the product of impedances of the other pair of opposite arms. We know that the impedances are the complex numbers. So Z1, Z4 equals to Z2, Z3. The phase angle of the first arm theta 1 plus phase angle of the fourth arm theta 4 is equal to the phase angle of the second arm theta 2 plus phase angle of the third arm theta 3. So phase angles of arm 1 and 4, the sum of that must be equal to phase angles of the arms 2 and 3. So this is the bridge balance conditions. The products of the magnitudes of the opposite arms must be equal. Next, the sum of the phase angles of the opposite arms must be equal. So these are the conditions for the AC bridge to be balanced. So we have already seen the different types of the bridges. Basically, there are two types of bridges, the DC bridges and the AC bridges. So the DC bridges are used to measure the resistance, while the AC bridges are used to measure the impedance consisting of the capacitors and the inductors. The AC bridges use the AC excitation voltage. The DC bridges use the DC excitation voltage. So the two types of DC bridges are the Wheatstone bridge and the Kelvin bridge. So Wheatstone bridge is used to measure the unknown resistance values, and the Kelvin bridge is used to measure the resistance value when the resistors are of less than 1 ohm. The various types of AC bridges are the Maxwell bridge, the shearing bridge, the Hayes bridge, the Wien's bridge, the Anderson bridge, the Owen bridge, etc. If you see the various uses of AC bridges, the Maxwell's inductance bridge circuit is used for the measurement of the unknown inductance in terms of the known capacitor value. It is preferred for coils with low Q values. If you come to Hayes bridge, it is used for measurement of the unknown inductance, and it is preferred for coils with high Q values. The shearing bridge is used for measurement of the capacitance. The shearing bridge is also used for measurement of the insulating properties. Wein bridge. A Wein bridge is used for measurement of the unknown frequency. It is used for measurement of unknown capacitance with great accuracy. So these are the different applications of the different meters. Now, coming to Maxwell's bridge. Maxwell's bridge, it is used to measure unknown inductance in terms of the calibrated resistance and inductance, or resistance and capacitance. Calibrated resistance, inductance, or calibrated resistance and capacitance. It uses the principle that the positive phase angle of an inductive impedance can be compensated by the negative phase angle of a capacitive impedance when put in the opposite arms and circuit is at resonance. That is, no potential difference across the detector and hence no current flows through it. The unknown inductance then becomes known in terms of the capacitance value. In a circuit, we can use two resistors R1, R4 to be the fixed value. R2 and C2 are variable. R2 and C2 can be adjusted until the bridge is balanced. So R3 and L3 can be calculated, where R3 and L3 are the series arm whose values are to be found out. R3 is given as R1 R4 by R2. L3 is given as R1 R4 C2. So, to avoid the difficulties associated with determining the precise value of a variable capacitor, sometimes a fixed value capacitor will be installed and more than one resistor will be made variable. It cannot be used for the measurement of high Q values. It is also not suited for the coils with low Q value less than 1, because there will be a balance convergence problem. So its use is limited the measurement of low Q values from 1 to 10. Q equals to omega L by R. The frequency of the AC current used to assess the unknown inductor should match the frequency of the circuit the inductor will be used in. The impedance and therefore the assigned inductance of the component varies with frequency. A practical issue in construction of bridge is its mutual inductance. Due to magnetic field of one intersects the coil of the other, it will reinforce the magnetic field in that other coil, distorting the inductance of both coils. So, let us see a circuit of the Maxwell bridge here. The Maxwell bridge is used to measure unknown inductance in terms of the known capacitance. One of the ratio arms has a resistance a capacitance in parallel, that is R1, C1 in our circuit. The other ratio arm has the fixed resistance value R2. The third arm has the variable resistance R3 for balancing the bridge. And at the final arm, the unknown inductance is connected. The general equation for the bridge balance is Z1 Z4 equals to Z2 Z3. Applying here, this becomes Zx, that is unknown impedance, inductor and resistor, equals to Z2 Z3 Y1, where Y1 is the admittance of arm 1. So here you can see R1 in shunt with C1 is one ratio arm, R2 is the other ratio arm, R3 is the standard resistor arm, Rx in series with Lx is the unknown impedance or the unknown inductance with its inbuilt resistance Rx to be found out. So, from the figure, we can see that Z2 is equal to R2, Z3 is equal to R3, and Y1 is equal to 1 by R1 plus J omega C1. So, substitution of these values in equation gives us Zx is equal to Rx plus J omega Lx, which is equal to R2 R3 into 1 over R1 plus J omega C1. Separating the real terms and the imaginary terms gives us Rx is equal to R2 R3 divided by R1, and Lx is equal to R2 R3 C1. I am repeating, the separating the real and imaginary terms from the bridge balance equation, we get Rx equals to R2 R3 divided by R1. Lx is equal to R2 R3 C1. So, this is how we calculate the unknown inductance value with its resistance. So, the limitations of Maxwell's bridge. The problem with this Maxwell's bridge is it is limited to the measurement of inductance of medium Q coils with Q lying between 1 and 10. The phase angles of the resistive elements in arms 2 and 3 add up to 0 degrees. So, the sum of angles of arm 1 and arm 4 must also add up to 0 degrees. The phase angles of the high Q coil will be very nearly 90 degrees positive, which requires that the phase angle of the capacitive arm must also very nearly 90 degrees negative. So, This Maxwell's bridge is unsuited for the measurement of the inductance of coils with a very low Q values. For balancing the Maxwell bridge, first we have to adjust R3 for inductive balance and then adjust R1 for resistive balance. So now we have seen what a Maxwell bridge circuit is, how to measure the unknown inductance, what are the limitations of the Maxwell's bridge. Next, let us see what assuring bridge is. Assuring bridge is a very important capacitance measuring bridge circuit. It is also capable of measuring dielectric loss of the capacitor in addition to its capacitance value. It compares the capacitance of an imperfect capacitor in terms of capacitance of a standard capacitor. We can represent an imperfect capacitor with its loss-free capacitance. Here it is C2 in series with a resistance. We normally use this type of bridge circuit for measuring capacitance at a very high voltage level. The shearing bridge is able to determine the quality of the capacitor in terms of its dissipation factor. Pure capacitor leads the current by 90 degrees, but an imperfect capacitor leads the current with a phase angle less than 90 degrees. The difference of the angle from 90 degrees is referred to as the defect angle of the capacitor. The tangent of the defect angle is called the dissipation factor of the capacitor. The ratio of the resistive component and the reactive component of a capacitor is the dissipation factor. Tan del is equal to omega R C2. Now, let us see what the shearing bridge consists of. It is used to measure the unknown capacitance. This bridge is useful for measuring the insulating properties, that is, phase angles very nearly equal to 90 degrees. The basic circuit arrangement is shown here. It contains parallel combination of resistor and a capacitor, standard arm which contains only capacitor. Now, the bridge balance condition is the sum of the phase angles of arms 1 and 4 equals the sum of the phase angles of arms 2 and 3. The sum of the phase angles of arms 2 and 3 will be 0 degrees plus 90 degrees, which is equal to 90 degrees. To obtain the 90 degrees phase angle needed for balance, the sum of the angles of arms 1 and 4 must equal 90 degrees. The power factor of a series RC combination is defined as the cosine of the phase angle of the circuit. The power factor of the unknown capacitance equals to Rx by Zx. For phase angles very close to 90 degrees, the reactance is almost equal to impedance, and we can approximate the power factor to Rx by Xx, which is equal to omega Cx Rs. The dissipation factor of a series RC circuit is defined as cotangent of the phase angle. Therefore, dissipation factor is equal to omega C. The quality factor of the coil is defined as Q equals to XL by RL. So the dissipation factor is reciprocal of the quality factor Q. Therefore, dissipation factor is equal to 1 by Q. By substituting the value of Cx in equation 1 and Rx in equation 2, we obtain D equals to omega R1, and we have discussed about the Maxwell's bridge and the Shearing bridge. So here in the Maxwell's bridge, it is used to measure the unknown inductance in terms of the calibrated resistance and inductance, or resistance and capacitance. It uses the principle that the positive phase angle of an inductive impedance can be compensated by the negative phase angle of the capacitive impedance when put in the opposite term, and the circuit is at resonance. That is, no potential difference across the detector, hence no current flowing through it. The unknown inductance then becomes known in terms of the capacitance. In terms of the Shearing bridge, it is a very important capacitance measuring bridge circuit. It is also capable of measuring the dielectric loss of the capacitor. In addition to its capacitance value, it compares the capacitance of an imperfect capacitor in terms of the capacitance of a standard capacitor. We can represent an imperfect capacitor with its loss-free capacitance in series with a resistance. We normally use this type of bridge circuit for measuring capacitance at a very high voltage level. The Shearing bridge is able to determine the quality of the capacitor in terms of its dissipation factor. Pure capacitor leads the current by 90 degrees, but an imperfect capacitor leads the current with a phase angle less than 90 degrees. The difference of the angle from 90 degrees is referred to as defect angle of the capacitor. The tangent of the defect angle is called the dissipation factor of the capacitor. The ratio of the resistive component and the reactive component of a capacitor is dissipation factor, given as tan del equals to omega R C2. Coming to a Maxwell bridge, to avoid the difficulties associated with determining the precise value of a variable capacitor, sometimes a fixed value capacitor will be installed and more than one resistor will be made variable in a Maxwell's bridge. So it cannot be used for the measurement of high Q values. It is also unsuited for the coils with low Q values less than 1 because of the balance convergence problem. Its use is limited to measurement of low Q values from 1 to 10, given as Q is equal to omega L by R. So, in a Maxwell bridge, The frequency of the AC current used to assess the unknown inductor should match the frequency of the circuit of the inductor which will be used in the impedance, and therefore the assigned inductance of the component varies with frequency. A practical issue in construction of the bridge is the mutual inductance due to magnetic field of one intersects the coil of the other. It will reinforce the magnetic field in that other coil, distorting inductance of both the coils. So this is all about the Maxwell's bridge and the shearing bridge. Thank you.